Okay, in this lecture, we'll continue our discussion on virtualization. We'll see what is hardware level virtualization. We will see types of hypervisor and hardware virtualization techniques. And some other virtualizations will also be looked into in this lecture. So basically, the term hardware level virtualization is used when the hypervisor um, gets directly installed on the hardware of the system. So it is a virtualization technique that provides an abstract execution environment in terms of computer hardware, on top of which a guest operating system can be run. So the computer hardware is virtualized in this type of virtualization. The guest is represented by the operating system. So the operating system is the guest operating system here. The host is the physical computer hardware. The virtual machine is represented by its simulation, and VMM by the hypervisor. So here the hypervisor allows the abstraction of underlying physical hardware. And we have seen in previous lecture that the physical hardware is abstracted by ISA. That means that in hardware level virtualization, which is also called as system virtualization, it provides ISA to virtual machines, which is the representation of the hardware interface of a system. This is different from process virtual machines, which exposes ABI interface to virtual machines. So if you say we are exposing ISA, that means the hypervisor sits right above the hardware, and if ABI is being exposed to virtual machines, that means the hypervisor is sitting on top of the host operating system. So let us look at the types of hypervisors. This will make the things more clear. So if you see here, we have hardware, we have ISA, and then on top of hardware, we have this level of indirection, which is virtual machine manager, VMM, or as we call it, hypervisor. This hypervisor abstracts this ISA to the virtual machine, and these are the virtual machines which will then run on top of this virtual machine manager. So let us see this. So hypervisor type 1 runs directly on top of the hardware. It is called as native virtual machine since it runs natively on hardware. So it is also called as bare metal hypervisor because it is installed directly on the bare metal, that is the hardware. So basically hypervisor type 1 is installed directly on the hardware. That is why it is called as native virtual machines, or it is also called as bare metal hypervisor. So in this hypervisor, if you look at this, it takes place of the operating system and interacts directly with ISA interface exposed by the underlying hardware. If you remember the traditional layered structure of a computing system, we had hardware, we had an operating system here, and on top of that was the applications. Now instead of hardware, on top of hardware, we have hypervisor. So hypervisor type 1 takes place of operating system and interacts directly with the ISA interface exposed by the underlying hardware. So they emulate this interface in order to allow the management of guest OS. So guest operating systems run in a less privileged mode in this type of architecture. The examples of type 1 hypervisors are Xen and VMware ESX. Type 2 hypervisors, on the contrary, they require the support of an operating system to provide virtualization service. So that means they utilize the functions which are available on host operating system to provide the virtualization service to virtual machines. So hypervisor type 2 are programs which are managed by the operating system and which interact with it through ABI, that is application binary interface. So what do these hypervisors do? They emulate the ISA of virtual hardware for guest operating system. So this type of hypervisor is also called as hosted virtual machine, since it is hosted within an operating system. So basically there are two types of hypervisors which we have discussed, type 1 and type 2. Type 1 hypervisors or the native hypervisors run directly on the host hardware and control the hardware and monitor the guest operating system. Whereas type 2 hypervisors or hosted hypervisors, they run on top of a conventional operating system and monitor the guest operating system. So let us look at the types of or techniques of hardware virtualization. We'll discuss three techniques. So we'll first look into full virtualization. Now to run operating system and application in virtual machines, and there are many such virtual machines which are sharing a physical infrastructure, the host operating system should supervise all such virtual machine. So what happens in full virtualization? In this, the virtualization layer completely decouples the guest operating system from the underlying hardware. So the guest operating system requires no modification and is not aware that it is being virtualized. Since it is completely decoupled from the hardware, it does not require any modification. So let's see, it enables full virtualization enables hypervisor to run unmodified guest OS directly on top of a virtual machine as though it were run on a raw hardware. This is because the guest operating system and the hardware are completely decoupled. So the guest operating system is completely decoupled from the underlying hardware, that is, it is unaware of being utilized. So what has to be done to make this possible? To make this possible, virtual machine monitors should provide emulation of the entire underlying hardware. They should completely emulate the underlying hardware. Now, the challenge here is that the privilege instructions have to be contained in the virtual machine. Now, we know what privilege instructions are. Privilege instructions are those instructions which can change the state of a hardware or they can access the input output ports of the hardware. So they have to be contained within the virtual machine. So the solution is to provide a virtual environment for all such instructions, thus posing some limit on the performance. And what is that virtual environment and how it is done? So as we've already seen in the last lecture, so and this can be enabled by direct execution of a non-privileged instruction and binary translation of privileged instructions. So let us see this. So we know that full virtualization does not need to modify the host OS. It relies on binary translation to trap and virtualize the execution of certain sensitive non-virtualizable instructions. So if we look at this diagram here, we have host or computer system hardware. So this is the hardware, and these are the rings, 4 rings. We know that ring 0 is the privileged ring, and this is the user mode. So this is the supervisory mode, and this is the ring 3 is the user mode. So in this, virtual machine manager is at ring 0 and the guest OS is at ring 1. Privileged instructions such as control and behavior instructions, they are trapped into a virtual machine monitor which will emulate the behavior of these instructions, and they will be then executed by the hardware. So the request, the non-privileged request, they are directly executed, but the privileged instructions which are there, they are trapped into VMM, and they are through binary translation, those requests will then be executed. So the method used in the simulation is called binary translation. So if you see, it combines binary translation of OS requests are basically privileged requests, and direct execution of user request or non-privileged requests. Next type of technique for virtualization or type of virtualization is para-virtualization. So para-virtualization involves explicitly modifying the guest operating system so that it is aware of being virtualized to allow near native performance. So in this, the guest operating system is modified to replace non-virtualizable instructions with hypercalls. So what happens in full virtualization, since the guest operating system is not at all aware that it is being virtualized, it seems as if it is running on the native system, so it issues privilege instructions, and since there are many such virtual machines, such privilege instructions may create problem. So in para virtualization, the guest operating system is modified. So it is modified in order to replace those non-virtualizable instructions with hypercalls. So the aim is to provide capability to demand the execution of performance critical operations directly on the host. So if you look at this, we have a host computer, that is the system hardware is here. On the hardware, on top of that, there is this virtualization layer. Ring 0 is the modified guest OS, and then in ring 3 we have user applications. So all the non-privileged instructions, they will run in the user mode. So, and those requests, there is a direct execution of those requests. They are the direct execution of user request. Whereas if you look at this, for the privileged instructions, hypercall to virtualization layer replaces non-virtualizable OS instructions. So that means this call, if there is a privileged instruction, it goes to virtualization layer. This is called as hypercall. So thus preventing performance loss that would otherwise be experienced in a managed execution. So what is the advantage of para-virtualization? It allows simpler implementation of virtual machine monitor that have to simply transfer the execution of these operations which were hard to virtualize directly to the host. So now these instructions, privileged instructions, will be simply passed on to the host through VMM. So to sum up, in para-virtualization, the guest OS is modified to enable communication with hypervisor to improve performance and efficiency. The guest OS is modified to replace non-virtualizable instructions with hypercall that communicate directly with the virtualization layer hypervisor. Next virtualization technique is hardware-assisted virtualization. So hardware-assisted virtualization refers to a scenario where hardware provides the architectural support for building a VMM which is able to run guest OS in complete isolation. So this technique attempts to simplify virtualization because full or para virtualization is complicated due to handling of privileged instructions. So in this, operating system can still run at ring 0 and hypervisor can run at ring 1. All the privileged and sensitive instructions are trapped in hypervisor automatically. So moreover, so basically this technique removes the difficulty of implementing binary translation in full virtualization. It also lets the operating system run in virtual machine without modification. So in hardware assisted virtualization, privileged and sensitive instructions are set to automatically trap to hypervisor. There is no need for either binary translation or para virtualization. Okay, so some comments on these techniques. So generally, hardware-assisted virtualization should have high efficiency. However, since the transition from hypervisor to guest OS incurs high overhead switches between processor modes, it sometimes cannot outperform binary translation. So even though in hardware assisted virtualization, binary translation of privileged instruction is not required, but then too sometimes it cannot outperform because of the high overhead switches between processor modes. Next point is that virtualization systems such as VMware now use a hybrid approach in which few tasks are offloaded to the hardware, but rest are still done in software. Finally, para-virtualization and hardware-assisted virtualization can be combined to improve the performance further. Let us look at what is partial virtualization. So, in partial virtualization provides partial emulation of the underlying hardware, thus not allowing the complete execution of guest operating system in complete isolation. So it does not emulate the complete hardware, it only partially emulates the hardware. So next, para-virtualization allows many applications to run transparently, but not all features of the operating system can support, as it will happen with full virtualization. An example of para-virtualization is the address-based virtualization used in time-sharing system. So this allows multiple applications and users to run concurrently in separate memory space, but they still share the same hardware resources, that is the disk, processor, and network. Next, let us look at what is storage virtualization. So, virtualizing storage means creating a virtual storage from a physical storage. When we spoke about if you remember the mini disks, which was the virtual disk, which was allocated to the virtual servers in IBM. So that's a kind of rough example for storage virtualization. So by consolidating all available storage devices in a data center, it allows creating virtual disks independent from device and location. So storage virtualization allows us to harness a wide range of storage facility and represents them under single logical file system. So what is storage virtualization? So I need some storage space. So I may be provided that storage space not in one physical location, since it may be possible that in one data center the complete demand of the user cannot be fulfilled. So some storage is given to the user in one data center, the other part of the storage is given to user in some other data center, and it's all and this is under one logical name, and it can be the user can access this through network. So basically, storage virtualization is pooling of physical resources from multiple storage devices into what appears to be a single storage. One of the most popular techniques is based on virtualization storage area networks. So storage area networks use a network accessible device through a large bandwidth connection to provide storage facilities. So storage area networks is like, we have various storages. They're all connected through high speed links, and a user can access can store their data or files in these storages, which can be in geographically different locations. That means user is in some other location. The storage can be in one or multiple distinct locations. Next, let us look at what is network virtualization. Network virtualization combines hardware appliances and specific software for creation and management of virtual networks. So it can aggregate different physical networks into a single logical network, This is called as external network virtualization. So the result of external network virtualization is, for example, a virtual LAN. So virtual LAN is aggregation of hosts that communicate with each other as though they are located under the same broadcasting domain. So let us see. So what is this network virtualization? So if I create, so usually what happens? A local area network is a network in which is within a certain is defined by a range, is connects the systems or devices which are within a few kilometers of geographical distance. So, but I can create a virtual LAN. For example, I can have some systems which are in Patiala campus in Thapar University, and I can have some systems which are in Deravasi campus of Thapar University. I can create a virtual LAN for these. So that means now when they will work, it will seem as if they are located under the same broadcasting domain, though they are geographically at different locations, but I have aggregated them under a same logical network. So this is called as external network virtualization. Network virtualization, another part to it is it can provide a network like functionality to an operating system partition. This is called as internal network virtualization. So what happens with this? Guests obtain a virtual network interface to communicate with. First, the guest can share the same network interface of the host and use network address translation to access the network. Second, the VMM can emulate and install on host an additional network device together with the driver. Third, guest can have a private network only with the guest. So let us look at this, what this is. So in internal network virtualization, so guest can obtain a virtual network interface to communicate with via three methods, via other guests. So one is through network address translation. So they can share the same network interface of the host. So the host has an IP address, let's say. So it has an IP address that is a public IP address. So that public IP address is mapped to a number of multiple private IP addresses through network address translation. So one private IP address is mapped to n number of private IP addresses, and each of this private IP address is given to the host virtual machine, the guest which is on that particular physical hardware, and through this they can access the network. The second issue can be or the way can be that the virtual machine monitor can emulate and install on the host an additional network device together with the driver. So in the first case, there was only one network interface card. There was only a single IP address, and that single public IP address was mapped to multiple private IP addresses through NAT. But in this virtual machine, in the second case, NAT is not being used. VMM can emulate and install on the host an additional network device together with the driver. Third is guest can have private network. So the third option is that they can have private private network only with the guests. So that means this network virtualization means it can provide a network like functionality to an operating system partition. So if there are multiple guests, all these are the various options on how they can access the network. So the next is desktop virtualization. So let us see what it is. Basically, desktop virtualization abstracts the desktop environment available on personal computer in order to provide access to it using client-server approach. So it provides the same outcome of hardware virtualization but serves a different purpose. Similar to hardware virtualization, desktop virtualization makes accessible a different system as though it were similar to hardware virtualization, desktop virtualization makes accessible a different system as though it were natively installed on the host. But this system is remotely stored on a different host and accessed through a network. So basically it addresses the problem of making same desktop environment accessible from everywhere. So that means if I have a system here and I need some other configuration, I need some if my system does not give me that configuration which I need to work on, what I can do is I can opt for desktop virtualization. So in that I'll have a virtualized desktop, and I simply need to log in and I'll get the desktop with that configuration which I desire, that operating system, that much CPU, that much memory, that is storage, and I can use it from anytime and anywhere. So because all I need to do is just log in, though that physically that desktop is not located on my system, but and I can actually access that virtualized desktop through any web enabled device. Generally, the desktop's environment is stored in a remote server or data center that provides a high availability infrastructure and ensures the accessibility and persistence of data. Therefore, an infrastructure supporting hardware virtualization is fundamental to provide access to multiple desktop environment hosted on same server. So basically, where are these desktop environments stored? They are stored in some remote server or data center, right? And they should be well connected through the network. So that means from where can I get this virtualized desktop? I can only get virtualized desktops from the servers who support full virtualization, because what I need is I need a complete system. I need a virtualized system. That is what I need is the hardware, that is storage, memory, CPU. I need the operating system and the applications, whatever are as per demand of the user. So a specific desktop environment is stored in a virtual machine image, and it is loaded and started on demand when the client connects to the desktop environment. This is a typical cloud computing scenario in which user leverages the virtual infrastructure for performing the daily task on his computer. So I think, yeah, and the advantage of this are high availability, persistence, accessibility, and ease of management. Because since the system which I have, this virtual system or virtual desktop, what it is being called, is stored in some server. So all I need is an internet connection and a web-enabled device to access that desktop from anytime, anywhere. Finally, let us see what is application server virtualization. So it abstracts a collection of application servers that provide the same service as a single virtual application server by using load balancing strategies. So let us see what it means. So I have multiple application servers. So they are all providing service. But now what I do is I logically, or virtually, combine these application servers into one. And now they provide, though they are providing the same service, but now they provide that service as a single virtual application server by using load balancing strategies. What is this load balancing strategies? So suppose I have I had 5 application servers, and I have created a single virtual server out of these 5 application servers. So now when a request comes, so load balancing, the basic aim of load balancing is that load in all these 5 servers should be equal. It is not that one of the servers should be very heavily loaded and the other server should be very lightly loaded. So load balancing, what it does is it maintains the load of all the servers at a same level. So if there are requests which are coming, so what will be done is there is a load balancer which does this load balancing. So load balancer will check load of each of the physical application server, though virtually they are one. It will check load of individually each application server, and will allocate that service request to that application server which is most lightly loaded. So this is called as load balancing strategy. Second, it provides high availability infrastructure for services hosted in application server. So this is important. See, if a user was being served by one application server and somehow that application server crashed, or maybe due to some fault, or there was some disaster. But now what happens is, now the user is being served by one virtual server. This virtual server is combined of 5 application servers. These 5 application servers can be may not be in the same location. They may be in geographically different locations. So now if one of these physical application server fails, the load can be taken up by other 4 servers. So anyways, the virtual server will stand and it will keep serving the users. If one of the physical application server has gone down, it will serve it through other 4. So it serves the same purpose of storage virtualization, that is providing a better quality of service rather than emulating a different environment. So we'll stop here. Thank you.